In a previous video, I talked about structural hazards, data hazards, forwarding, and how to stall the pipeline. In this video, I will talk about control hazards. I will show you how to implement the jump and the branch instructions in the pipeline. And I will talk briefly, I will introduce a branch prediction. So what is needed to calculate the next PC address? Well, first we need the opcode, because the opcode is going to tell us whether the instruction is a jump, is it a branch, etc. So we need the opcode. If the opcode is a jump or a jump and link, we know that this is an unconditional jump. All what we need is the 26-bit address. This 26-bit address, which is encoded inside the jump instruction, is the jump target address. The difference between jump and link is that the jump and link is going to save the return address, which is the address of the next instruction in memory. This will be PC plus 4. So the value of PC plus 4 will be saved in register R31. It's always R31. This is implicit in the jump and link instruction. Now, if the instruction is a jump register, we can tell this from the opcode and the function code. Then what we need is that we need the address, which is in register RS. So the address is not an immediate. The address here is the value of register RS. And this is where we need to branch. Sorry, this is where we need to jump in the case of a jump register. Now we have here two instructions, jump register, and we have a jump and link register. The difference between the two is that jump and link register is going to save the return address, and you can save it in any register, destination register RD. Now, if the opcode indicates that this is a conditional branch, I need two things. I need the branch outcome. I need to determine if the branch is taken or not taken. Okay, this is one thing. I need to know the outcome. In addition, I need to determine the branch target address. And the branch target address is computed based on the value of the PC and the 16-bit offset. So it is PC relative addressing. So the offset here can be positive or negative, indicating whether the branch is a forward branch or a backward branch. Now, how about the remaining instructions? The remaining instructions are not really a jump or a branch. So all what we need is just to advance the PC value to point to the next instruction in memory. So instructions are executed sequentially. So every time we finish one instruction, we move to the next one, except when we have a jump or a branch. Now, the opcode is decoded in the instruction decode stage. So first we have to fetch the instruction. And then during the second stage, which is the instruction decode stage, we can examine the opcode. And then we can tell if the instruction was a jump or a branch. At this point, we already have the next instruction is being fetched in the first stage of the pipeline. So by the time we have updated the program counter, already we have the jump delay, which is equal to 1 cycle. So this is the delay from the time we have decoded the instruction until we have updated the PC. Already we have the next instruction in the pipeline. Now this instruction that appears after a jump is not really supposed to run, and it's not really supposed to update any register in the register file or to store anything in the data cache. So this instruction has to be converted into a bubble. In the case of a branch, okay, the branch outcome is computed in the execute stage, in the third stage of the pipeline. So by the time we have executed the branch and updated the program counter, okay, already we have wasted 2 clock cycles, and already we have 2 instructions in the pipeline. So this is explained clearly in the next slide. Okay, so this shows the 2-cycle branch delay. Suppose I have a branch instruction, for example, a branch if equal. Okay, so the instruction is going to be fetched at clock cycle number 1. We are going to fetch this instruction from the instruction cache. At clock cycle number 2, we are going to decode the instruction. Okay, so the opcode will be examined. The opcode indicates that this is a branch if equal instruction. We are also going to read R8 and R9 from the register file. Now, at clock cycle number 3, we are going to execute the branch instruction. Now, while we are executing the branch instruction, already we have fetched at clock cycle number 2, we have fetched the next instruction that appears after the branch if equal at clock cycle number 2. And at clock cycle number 3, we are going to fetch the second next instruction. So already I have next 1 and next 2 in the pipeline. Now, suppose that the branch instruction is taken. So, but after executing the branch, we are going to update the program counter according to the branch target address, but this will be updated at the end of clock cycle number 3, at which point we have next 1 and next 2 in the pipeline. Now, we cannot allow next 1 and next 2 to complete and write the results into the register file, or if we have a store instruction, we cannot allow the store instruction to update or to store the data in the data cache. So for this reason, what we have to do is that we have to convert next 1 and next 2 into bubbles. So we have to kill these 2 instructions. And therefore, when we convert them into bubbles, they will have no effect on the pipeline, and they will not really update the state of the pipeline. So this way we can get rid of next 1 and next 2. So next 1 and next 2 will exist in the pipeline. Already we have fetched them, but what we have to do is that we have to convert them into bubbles so that they don't really have any effect on the state of the pipeline. We can also have a situation in which the branch is not taken. So we have 2 possible outcomes for the branch. Either it is taken or not taken. If the branch is taken, already we have seen this in the previous slide, we have to convert next 1 and next 2 into bubbles. But what if the branch is not taken? Already we have next 1 and next 2 in the pipeline. So should we really convert them into bubbles? The answer is no. We allow these 2 instructions to proceed normally in the pipeline because the branch is not taken. So just allow these 2 instructions to proceed normally in the pipeline and write their results into the register file, or even update the data cache if we have a store instruction. So in this case, there are no wasted clock cycles, which is great. Okay, so if the branch is not taken, we don't waste clock cycles. If the branch is taken, we lose 2 clock cycles, so we have to convert the next 1 and next 2. These 2 instructions have to be converted into bubbles. Let us understand now how the jump and the branch instruction can be implemented in the pipeline. So we have here I'm going to focus on only 3 stages of the pipeline. The first stage, where we have the instruction cache, we have the program counter, we have the multiplexer at the input of the PC. So this is the first stage. The second stage, we have the instruction. Okay. So first we are going to fetch the instruction from the instruction cache during the first stage of the pipeline. In the second stage, we have the instruction stored inside the instruction register. So let us focus here on the second stage of the pipeline, where we have the instruction. Now we can examine the opcode. The opcode is going to be decoded by the main control logic. If this instruction was a jump, okay, we will have a jump control signal. This jump control signal is going to be wired to the PC control. Okay, so that's the same wire. Okay, that's the jump control signal. This indicates that the second stage of the pipeline has detected a jump instruction. We have a jump instruction in the second stage of the pipeline. So what will happen here is that we have to extract the jump target address from the jump instruction. It is just a 26-bit address. And then this address will be used to update the PC. So this jump target address is connected to input 1. PC source has to select input 1. And therefore, we are going to update the PC according to the jump target address. And this is how the jump will take place. But the problem is that already we have an instruction which is being fetched here. This is the next instruction that appears after the jump. It appears at the output of the instruction cache. Already we have fetched this instruction. This is the instruction that immediately appears after the jump. Now, we cannot allow this instruction to proceed into the pipeline. So in this case, what I have to do is that I have to kill the next instruction that appears after the jump. How do I kill this instruction? The PC control is going to generate a kill control signal. This is called kill 1. And this kill 1 is going to be connected to a multiplexer. This multiplexer is going to select a bubble. The bubble is just a no operation. So rather than selecting the instruction at the output of the instruction cache, we are going to select a bubble. So the next instruction that will be in the instruction register will be a bubble. So a bubble is just an operation. For example, it could be an ALU R type instruction that writes the result into R0. So as long as we are writing the result to R0, then basically this instruction has no effect on the pipeline. It does not update any register in the register file. So a bubble can be any instruction that writes to R0, any ALU instruction, okay, can write to R0, okay, can be used as a bubble. So this is what we have to do in the case of a jump. We waste one cycle because the instruction that was fetched is not used. So we are injecting a bubble into the pipeline in the case when the instruction is a jump. Now, how about a branch instruction? Okay. In the case of a branch instruction, okay, we are going to decode the branch during the second stage of the pipeline. We can even calculate here the branch target address. So I'm using here in the second stage of the pipeline, I'm using an adder. The output of this adder here is the branch target address. So we can early compute the branch target address, assuming that the instruction is a branch, based on the extended immediate constant. So here the input to this adder will be the extended immediate constant and also the incremented PC. So this is how the branch target address is defined in the MIPS architecture. It is PC relative, and this is why we need this adder to calculate the branch target address. Now, this is not enough. I need to know what is the outcome of the branch. So I have to wait until the third stage of the pipeline where we have the ALU. So I have to read the values of register RS and RT. So these will be sent to the third stage. I will have their values in A and B. And these values are sent to the ALU. Now, the ALU can make a simple comparison. For example, it can subtract the value of A minus B to check if the result is 0 or not 0. 0 indicates that they are equal. Not 0 indicates they are not equal. So what I need in the case of a branch, I need the branch control signals, branch if equal, branch not equal. These are generated by the main control. They are passed to the execute stage. The execute stage is going to wire them back to the PC control. The execute stage is going to execute the branch, is going to determine the 0 flag. The 0 flag is also sent back to the PC control. The PC control will determine if the branch is taken or not taken. If the branch is taken, it's going to select the branch target address. So this will be input 3. This will be the branch target address. But by the time we have selected the branch target address, we have the next one and next two instructions in the pipeline. So these two instructions both have to be killed. So we need kill 1 and we need kill 2. So the kill 1 here, okay, so the kill 2 is going to kill the instruction which is in the second stage of the pipeline. This will be the next instruction appearing after the branch. The branch is now in the execute stage. The next one will be in the second stage of the pipeline, so it's actually being killed. And also the second next is being killed also. It is at the output of the instruction cache. So we are killing two instructions, not just one. So here we are injecting a bubble, okay, into the instruction register. At the same time, we are injecting a bubble here into the third stage of the pipeline. So that's how we implement branch instructions. Finally, we have the jump register. In the case of the jump register, we have to wait until we have read the value of source register RS its value will be available in register. It will be available in A. This will be the pipeline register A. So we pass the jump register address back to input 2 of the PC. Again, we have to kill 2 instructions, kill 1 and kill 2, because these 2 instructions will exist in the pipeline at the time when we have updated the program counter and the jump register took place. Let us now examine the impact of the jump and the branch instructions on the CPI. We would like to see how does this impact the performance of the pipeline. So consider a 5-stage pipeline in which the base CPI is equal to 1 without counting the jump and the branch stall cycles. Now assume that 5% of the instructions are unconditional jump and 20% of the instructions are conditional branch. Now it says that 90% of these conditional branch instructions are taken and the remaining 10% are not taken. So we only waste cycles if we have the branch is taken. If the branch is not taken, we don't waste any clock cycles. It says that 1 stall cycle per jump because the jump is always taken, and we have 2 stall cycles if we have a taken branch. Now, what is the impact of the jump and the branch instructions on the CPI? This is the question. Well, the answer is simple. If we have a jump instruction, every time we have a jump, then we waste 1 clock cycle. So therefore, we are going to add 1 stall cycle for 5% of the instructions. So we multiply 1 cycle here by 0.05. In the case of a branch, we only add 2 cycles because we have 2 stall cycles in the case when the branch is taken. So 90% of the instructions are 90% of the branch instructions are taken. So we have 20% are branch and 90% of these 20% are taken. So we multiply 2 stall cycles by 20%, which are the branch instructions, and we multiply it by 90% because 90% of these branch instructions are taken. So we get 0.36. So therefore, if we would like to calculate now the new CPI, okay, counting the jump and the branch stall cycle, so the new CPI will be 1 plus the 0.05, which is caused by jump instructions, plus the 0.36, which is caused by the taken conditional branch instructions, and therefore the new CPI will be 1.41. So the CPI went up from 1 to 1.41, and this is going to slow down the execution, it's going to increase the execution time of the program. So far, we have seen one way of implementing the jump and the branch instructions. We have predicted the branch to be not taken. This was described in a previous slide. So the idea here is that if the branch instruction is not taken, we do not kill the instruction, the 2 instructions that appear after the branch if the branch is not taken. However, we kill the instruction that appears immediately after the jump or after the branch which is taken. In the case of the jump, we kill only the next. In the case of the taken branch, we kill 2 instructions, the next and the second next. Okay, so this is if the branch is taken. This is one way of implementing the jump and the branch. And if we do it this way, we lose some performance because every time we have a jump, we are going to waste 1 clock cycle. If we have a taken branch, then we are going to waste 2 clock cycles. We are going to convert the next 2 instructions into bubbles. People have thought about different ways of implementing a branch, and they came up with some alternatives. One way to implement the branch is called delayed branching. So here we define the branch to take place after the next instruction. Okay, so the branch does not take place immediately, we allow one instruction to appear after the branch, and this instruction is allowed to proceed in the pipeline to execute and complete normally. So here the compiler is responsible to fill the branch delay slot, and only one slot is used. I'll talk about delayed branching in the next slide. There is another alternative which is being used today in all modern CPUs, which is called dynamic branch prediction. So I will introduce dynamic branch prediction in the next few slides. Let me first talk about delayed branching. This idea appeared in early pipelines. The idea is to define the branch to take place after the next instruction. Okay, so the branch does not take place immediately, it is delayed. So here, the processor or the architecture is going to define one delay slot, and the idea is to reduce the branch penalty. So the compiler, the software here, has to fill the branch delay slot with a useful instruction. Let us take a look at this example. I have this branch if equal instruction. Okay, so this branch is going to branch to label. That's a backward branch. It's a loop branch. It does not really matter. This branch can be forward or backward. It does not really matter. It will work in both cases. So the compiler has to find an instruction, an independent instruction. For example, this add instruction is going to write its result to R8, and the branch does not read R8, so the branch does not depend on the add instruction. So the idea is to move this add instruction into the branch delay slot as shown here. So the compiler is going to fill the branch delay slot, is going to reorder the instructions. It's going to move the add instruction, which is supposed to be executed before the branch. It's going to be moved after the branch into the branch delay slot. So whether the branch is taken or the branch is not taken, in both cases, the add instruction will be fetched, it will be executed, and it will be completed. Its result will be written to R8. So the pipeline is not going to kill this add instruction. It's going to allow this add instruction to proceed in the pipeline normally. So this way it can avoid, or it will not waste a clock cycle. So the idea is to improve the performance of the pipeline. In the worst case, if there is no instruction found from before the branch that can be moved into the branch delay slot, then the compiler can fill the branch delay slot with a no op. So this is really the idea of delayed branching. So we're not really branching immediately. We are delaying the branching after fetching and executing the next instruction. Now, people have implemented delayed branching in the past, but there is a major drawback of delayed branching. There is a new meaning of the branch instruction. So we are changing the meaning of the branch instruction. So the branch instruction does not take place immediately. It takes place after the next instruction. Okay, so we have modified the meaning of the branch instruction, and because we are modifying the meaning, this is going to impact the software. It's going to impact the compiler. So now the compiler is responsible to fill the branch delay slot. So people have to go and modify the compiler, okay, to fill the branch delay slot. And this is not really nice from the compiler writer, from the compiler point of view. The compiler writer might not be happy because he has to go and modify the compiler to fill the branch delay slot. Another major drawback, okay, of delayed branching is that in modern processors, okay, modern CPUs are deeply pipelined. So in this presentation, I talked about a 5-stage pipeline, but in reality, the pipeline is deep, and therefore it might be 10 or more stages in the pipeline, and in this case is going to increase the branch delay. So if the branch delay is increased to multiple cycles in deeper pipelines, then this means that the branch penalty is going to increase, and it will be difficult to fill multiple delay slots. Okay, we cannot allow to have multiple delay slots after the branch because this is going to complicate the software and the compiler, and it will be very difficult to fill these multiple delay slots with useful instructions. So for this reason, people no longer used the concept of delayed branching. So it was used in earlier pipelines. However, today dynamic branch prediction has replaced the old concept of delayed branching. So in the next slide, I'm going to introduce dynamic branch prediction. Okay, so now I would like to introduce the concept of dynamic branch prediction. So the idea is to predict the outcome of the branch at runtime. But it's not enough to have the outcome, to predict the outcome. I also need the target address of a branch. So in the case of a branch, I need two things. I need to know the target address of the branch, and I need to know what's the outcome of the branch, if the branch is taken or not taken. So these two things are needed. So how can we branch with zero delay? Okay, this is really the big question. How can we do the branching in the first stage of the pipeline without any delay? So all what we have in the first stage of the pipeline, we have the program counter. Okay, that's all what we have. We have also, of course, the instruction cache, but the instruction itself does not exist in the first stage of the pipeline. So first we have to fetch it, and then we can examine, we can decode the instruction in the second stage of the pipeline. So if we wait until the second stage of the pipeline to decode the instruction, at that time we'll be fetching the next instruction from the instruction cache. So the idea here is that I would like to have the branch to take place, okay, with zero delay in the first stage in the pipeline. So how to do this? So people came up with this idea, which is called the branch target buffer. Okay, so the branch target buffer, it is a small cache. Again, every time we talk about something, we introduce a cache. It's a small cache, which is really used to store the target address of recent branches and jumps. So here, when I talk about the branches, I'm talking about the branches as well as jumps, because also we can do the same thing with the jump instructions. So what we are storing the addresses of recent branch instructions. So only the addresses of the branch and the jump instructions are stored inside this buffer, which is a small table, as well as the target addresses. So every time we encounter a jump or a branch instruction in the program, we store the address of the jump or the branch inside this buffer. We also store the address of the target of the jump, where I would like to jump, the target address of the jump or the branch instruction inside this buffer. Now there is a third column here which indicates the predict bits. Okay, we need this predict bits to predict if the branch is taken or not taken. So the third column is used by branch instructions only to predict if the branch is taken or not taken. In the case of a jump, the jump is always taken. So we don't really need the predict bit, or we can always set the predict bit to 1 in the case of a jump. But in the case of a branch, it may or may not be taken. So this is why we need this column. Now, what will happen is that at runtime, so the content of this branch target buffer is filled dynamically at runtime because it's like a cache, it's small cache, which is needed for branch prediction that will store the target address as well as the prediction bits. So what we need is that we need to fill the content of this branch target buffer at runtime, exactly the same way that we fill the content of a cache at runtime. So at runtime, we only have the program counter in the first stage of the pipeline. So we can use the lower bits of the program counter as an index, okay, to this branch target buffer. So we can use this as an index. And what we can do is that we can compare the upper bits of the program counter against the address of the recent branch. So we're using here the address of the recent branch as a tag. So we can actually see if there is a match. If there is a match, then we have the target address. So we use a comparator here that can compare, okay, the value of the program counter against the address of the recent branches. Okay, and if there is a match, we already have the target address inside the branch target buffer. Okay, so we need also to look at the prediction bits. So if we have a match and the branch is predicted to be taken, then we select the target address. So the target address here is available at this input of the multiplexer. And if the address is not found inside the branch target buffer, if it's not the address of a branch or a jump instruction, or the entry does not exist inside this branch target buffer, then we simply increment the PC so that we can point to the next instruction in memory, and we fetch the next instruction in memory. So by having this branch target buffer in the first stage of the pipeline, so in addition to the instruction cache, I need to have this branch target buffer in the first stage of the pipeline. I can reduce the jump delay or the branch delay to 0. Now I know that jumps are always taken, so therefore I can jump with 0 delay. Now in the case of branches, I need to predict the outcome of the branch. If the branch is predicted to be taken, then the branch will be taken with 0 delay. But we need to also verify if the outcome, this is only a prediction. In the case of a branch, it's only a prediction. We still have to verify the true outcome of the branch. So we still have to execute the branch instruction in the third stage of the pipeline. And if the prediction is correct, we continue with normal execution. However, if the prediction was incorrect, then we have to kill the instructions that were fetched along the wrong path, okay, in the program, and we have to modify the program counter to go along the correct path inside the program. And this way we lose cycles if we have a misprediction. This slide summarizes the branch target buffer that I described in the previous slide. So remember that the branch target buffer is a small cache. What we are storing the address of the recent jump and the branch instructions. These are used as tags, okay? They will be matched against the PC. We are storing the target address of the jump or the branch so that the jump or the branch can take place with 0 delay. Okay, we can update the program counter with 0 delay. We are also storing prediction bits. These are needed for conditional branch to predict if the branch is taken or not taken. So we use the lower bits of the PC to index the branch target buffer. Okay, so this is the same way that we index a cache, and we compare the PC against the entry in the branch target buffer. Okay, so we use a comparator to see if we have a hit or a miss. Hit means that we found the entry in the branch target buffer. A miss, it means that the entry was not found. Okay, so these branch target buffer entries are updated by the hardware at runtime. So now we understand what dynamic branch prediction means. We are trying to predict the outcome of branches at runtime. We are using prediction bits. Now, these prediction bits can be associated with each entry in the branch target buffer. So each entry will have its prediction bits. So these prediction bits will reflect the history of a branch instruction. So we are using the history of a branch to predict the future of a branch instruction. Now, as a minimum, I need one prediction bit per entry. This prediction bit will indicate the last outcome of a branch. But to have a higher accuracy, people use more than one prediction bit. So typically people use 2 prediction bits per entry to improve the accuracy of branch prediction. Now, we don't know if the prediction is correct or not. If we have a correct prediction, then we can continue normal execution. And in this case, we don't have any wasted clock cycles. Okay, so this will be great, and the pipeline can run at maximum performance. However, if we have incorrect prediction, which is called a misprediction, we have to kill the instructions that were fetched along the wrong path. Okay, so these instructions, we have to kill them, and therefore we waste clock cycles. And then what we have to do is that we have to update the branch target buffer. We have to update the prediction bits. We have to change the program counter, and we have to go along the correct path. So this way we are wasting clock cycles, but we are making this update in the case when we encounter the same branch again in the future, we'll have a correct prediction. This slide summarizes dynamic branch prediction in the first three stages of the pipeline. So this is the first stage, which is the instruction fetch stage. Then we have the second stage, which is the instruction decode stage. And this is the third stage, which is the execute stage. Now, during the first stage of the pipeline, we have the program counter. This program counter PC register is used to address both the instruction cache and the branch target buffer. So the same address is sent to the instruction cache to fetch the instruction, and the same address is used to address the branch target buffer to see if there is a match. So if there is an entry in the branch target buffer that matches the PC address. Now, in the case of the branch target buffer, either we can have a hit or we can have a miss. If we have a hit, it means that we have an entry in the branch target buffer. Now, if this entry is predicted to be taken, so here we check if there is predict taken. So either we have yes or we have no. So yes means that we have found an entry in the branch target buffer, okay, which is predicted to be taken. So the branch will be taken, and therefore the PC becomes the target address, and this is done with zero delay in the first stage of the pipeline. This can be the case if you have a jump instruction, which is predicted to be always taken. And it can also happen in the case of a branch instruction, which is predicted to be taken. Now, you can also have the situation in which there is no entry in the branch target buffer, okay, for this PC address. So either the entry does not exist, or there is an entry, but it says that the branch is predicted to be not taken. So in this case, we just simply increment the PC and we fetch the instruction at the next address. So this is what is really happening in the first stage of the pipeline. Now, the next stage is going to, the next two stages, the instruction decode and the execute stage, are going to verify whether the prediction is done properly in the first stage of the pipeline. So in the second stage of the pipeline, okay, we can examine the opcode. We can check if there is, from the opcode, if the instruction was a jump or a branch. In the case of a jump, if the instruction was a jump, okay, and we did not even find this jump entry inside the branch target buffer, if this is the case, then what we have to do is that we have to enter the jump address, the address of the jump instruction, and also we have to enter the target address. So we have to have an entry in the branch target buffer for this jump instruction, okay, and its target address. We have to kill the fetched instruction. So the next instruction is already in the pipeline, is being fetched. So we have to kill this fetched instruction, and then we have to restart the PC at the jump target address. Okay, so that's what has to be done if we discover that there is a jump instruction in the instruction decode stage. Now, if we discover that we have a branch instruction, we have to wait until the execute stage to check if the branch is taken or not taken. So if we discover that we have a branch, okay, then we have to see if what is the outcome of the branch. If the branch is not taken, then we can continue normal execution without wasting any clock cycles. And because already we have incremented the PC, so we don't really waste any clock cycles because the branch is not taken. However, if the branch is taken, okay, what we have to do is that we have to enter an entry in the branch target buffer in case this entry does not exist. So we enter the branch address, we enter also the target address of the branch, and also we set the prediction bit, okay, in the branch target buffer entry. We kill the two instructions that were fetched, Okay, so these are the next two instructions that appear after the branch, and we restart the PC at the target address of the branch. Now, we can also have the other possibility in which we have predicted the branch to be taken. So here we can go to the right. And in the case of a jump, the jump is always taken, so we don't really have to do anything. But in the case of a branch, and we have predicted the branch to be taken, now we reach the third stage of the pipeline. Again, we have to check if the branch is taken or not. So we have to verify whether the prediction was correct or not. So we predicted in the first stage that the branch is taken. We have to verify this prediction. Now, if the prediction is correct, the branch is taken, then we have a correct prediction, and therefore there are no stall cycles, and we can continue normal execution of the program. On the other hand, if the branch is not taken, we have a mispredicted branch. So what we have to do is that we have to kill the fetched instructions along the branch target address. So we have to kill these fetched instructions. So these two instructions that are already in the pipeline should be killed. We have to update the prediction bit, okay, in the branch target buffer, and we have to restart the PC to continue after the branch instruction. The simplest way to implement branch prediction is to use a one-bit prediction scheme. What this means is that we are going to use only one bit per branch instruction in the branch target buffer. So we associate one bit per branch instruction. So the value of this bit can be 0 or 1. It will record the last outcome of the branch instruction. So if the last outcome was not taken, we store a 0. If the last outcome was taken, we store a 1. So 0 here means that we are predicting the branch to be not taken, and 1 means that we are predicting the branch to be taken. So we are using the last outcome of the branch to predict the future behavior of the branch instruction. So because we have a single bit, we have two states. And if we are in a predict taken and the true outcome is taken, we remain in the same state. The same thing if we are predicting the branch to be not taken and the true outcome is not taken, then also we remain in the same state. If we are in predict taken and the true outcome is not taken, so we change the state. Similarly, if we are predicting the branch to be not taken and the true outcome is taken, we also switch states. Now, the problem with the one-bit predictor is that its accuracy is low. In other words, it can cause many mispredictions. In order to, for example, suppose that we have a nested loop. Okay, so loops can really be predicted with high accuracy. So in this example, we have an outer loop and I have an inner loop. If you look at the inner loop, we have here a branch instruction that will branch to the inner loop. This branch instruction is going to be mispredicted twice. During the first iteration, okay, it's going to be mispredicted, and during the last iteration, it will also be mispredicted. In the last iteration, it's very clear because we are going to predict the branch to be taken, but in the last iteration, it will be not taken, and therefore we'll have a misprediction. But then when we loop back, when we re-enter the inner loop and we start the first iteration, okay, so we are going to predict the branch to be not taken, but it will be taken, and therefore we have also a misprediction in the first iteration. So two mispredictions in the inner loop branch instruction for the first iteration as well as for the last iteration. Now we can do better by using a 2-bit predictor scheme. This is explained in the next slide. So in the in the 2-bit prediction scheme, we are using 2 bits. Okay, so with for each branch instruction in the branch target buffer, we are using 2 bits to predict the outcome of the branch. So using 2 bits, you can have 4 possible values. So 4 states. So the value of the 2 bits can be from 00 to 11, or in other words, from 0 to 3 in decimal. So 0 and 1, if the value of the bits are 0 or 1, it indicates that we are predicting the branch to be not taken. If it is 2 or 3, then we are predicting the branch to be taken. So here, predict taken is shown in green, and predict not taken is shown in red in the state diagram. So the way that this works is that the 2 bits are implemented as a saturating counter. So it goes from 0 to 3. So every time the branch is taken, we increment the counter. Okay, so we can start here at 0 and it can be taken, then it's going to increment it to 1, then another taken is going to take it to 2, and 3 is going to make it 3. It will saturate at 3. So every time the branch is taken, then we increment the counter, and therefore it's going to saturate at 3. In the case when the branch is not taken, if the true outcome is not taken, we decrement the counter. So it will go from 3 down to 2, then down to 1, and then down to 0. Okay, this is if the true outcome of the branch is not taken. And then as long as it is not taken, it will saturate at 0. So this is how it works. This is the 2-bit prediction scheme. It's very simple to implement in the hardware, and it works better than the 1-bit prediction scheme. So for example, if we have an inner loop and an outer loop, in the case of the inner loop, we will actually end up in strong predict taken. So the value of the 2-bit prediction scheme, the value of the 2 bits will be 3. And we are ending up here in the state which is strong predict taken in the case of a loop, because the loop iterations are always taken. Now, in the last iteration, we have the branch is not taken. So we go from strong predict taken to weak predict taken. Okay, so the counter will be decremented. The 2-bit counter will be decremented from 3 to 2. And then when we re-enter the inner loop, it's still predict taken. It's a weak predict taken. So the true outcome is taken, and therefore we go back to the strong predict taken. So we are switching between the weak and the strong predict taken in the case of the inner loop, and basically we are always predicting the loop to be taken. So only have one misprediction in the last iteration of the loop. Rather than having 2 mispredictions, we are reducing this to only 1 misprediction. Let us evaluate the 3 different branch schemes that we have seen so far. So we have seen predict branch to be always not taken. We have seen delayed branching. And also we have seen the dynamic branch prediction using the branch target buffer. So these are the 3 schemes that we have seen so far. So in this problem statement, it says that the penalty of the jump is 2 cycles. In other words, every time we have a jump instruction, then what we have to do is that we have to kill the next 2 instructions, not just the next one, but the next 2. So this pipeline is slightly deeper, and the instruction fetch is 2 stages, not just 1 stage. So this is going to increase the penalty of the jump. In the case of a taken branch, the penalty is increased from 2 cycles to 3 cycles according to this problem statement. So therefore, every time we have a branch which is taken, we have to kill the next 3 instructions in the pipeline. In the case of delayed branching, we can reduce the penalty because we can use the branch delay slot. So therefore, the penalty of the jump is reduced from 2 to 1 cycle. And the penalty of the taken branch is reduced from 3 cycles to only 2 cycles. Now notice that there is no penalty for a branch which is not taken, because by default, okay, so it is just 0 cycles in the case of the branch which is not taken, because remember that in the case of a branch which is not taken, already we have the instructions in the pipeline, so we are not going to kill them if the branch is not taken. Now the last scheme here is about dynamic branch prediction. In the case of dynamic branch prediction, we have a penalty only when we have a misprediction. So when we have a misprediction, the penalty is the same. It's going to be 2 cycles, okay, for a jump. It's going to be 3 cycles for a branch, whether the branch is taken or not taken. In both cases, if we have a misprediction, then the penalty is going to be equal to 3 cycles. Now, in order to solve this problem, I need to know what is the frequency of the instructions in the program. So we're going to assume that 3% of the instructions are jump instructions, 5% are branches which are not taken, and 15% are branches which are taken. In other words, we have 20% of my instructions are branch instructions, 5% are not taken, and 15% are taken. We also need to know, okay, what is the hit rate in the branch target buffer? So the hit rate here is given as 90% in the branch target buffer for both the jump and the branch instructions. In other words, 10% is the miss rate. Okay, so 10% of the jumps and the branches are not found in the branch target buffer, but later we are going to insert them in the branch target buffer. So remember that the branch target buffer is just a cache, a simple cache, and therefore the hit rate is given here as 90%. Now the accuracy for the jump, okay, so the accuracy for the jump is 100%. This is the prediction accuracy because all the jump instructions are always taken. So therefore, we can predict them with 100% accuracy. In the case of a conditional branch, okay, the accuracy is given here as 80%. Okay, so 80% of the conditional branch instructions are predicted correctly and 20% are mispredicted. So the question is, what is the impact on the CPI? Okay, so let us take a look at these three different schemes and see how they increase the CPI. The ideal CPI is given to 1, but because we have a penalty for the jumps and we have mispredictions in the case of branch prediction, then we have the CPI is going to increase due to the wasted clock cycles. Okay, so here's the solution. So remember that 3% of the instructions are jump, 5% are branches which are not taken, and 15% are branches which are taken. So let us take a look at the first scheme, which is predict not taken. So in this scheme, every time we have a jump instruction, we are going to lose 2 clock cycles. So the next 2 instructions have to be killed, and therefore we are going to waste 2 clock cycles. So therefore, we have to multiply 0.03 by 2. This is the number of stall cycles per jump instruction, okay, and 3% are jumps. In the case of branches which are not taken, okay, there are 0 stall cycles because we don't really kill any instruction. And in the case when we have branches which are taken, we have 15% of the instructions are branches that are taken. And every time we have a taken branch, the penalty is equal to 3 cycles. So therefore, we have 0.45 stall cycles per instruction. So if you add 0.06 here plus 0.45, we get the 0.51. So now the CPI is increased to 1.51. Okay. Now this is the CPI when the prediction scheme, when the branch scheme is predict not taken. Okay, for the next scheme, the delayed branch is going to reduce the penalty. So by reducing the penalty, okay, from 2 to 1 cycle in the case of a jump, we are reducing here the wasted clock cycles. So we multiply 0.03 by 1. Also, we are reducing the penalty in the case of a taken branch from 3 cycles to 2 cycles. So therefore, this is going to reduce the wasted cycles. So therefore, we are going to increase it from 1 to 1.33. Okay, so 0.33 here are the wasted cycles per instruction due to the instructions that are killed after the jump and the taken branch. Now the last scheme is the branch, okay, the branch prediction scheme using the branch target buffer. Now here the analysis is slightly different because only we lose, okay, when we have a misprediction. In the case of a jump, only when we have a miss in the branch target buffer, okay, it says that the hit rate in the branch target buffer is 90%. So only when we have a miss, so the miss rate is 10%. So when we miss here, okay, so 3% are jump instructions and 10% is the miss rate in the branch target buffer. So only when we miss, we have the penalty is equal to 2 cycles. When we have a hit, then we can reduce. Okay, so there are no stall cycles and we can there is no delay for the jump instruction. So therefore, only when we have a miss in the branch target buffer and the miss rate is 10%, so in this case, we are going to waste 2 clock cycles. In the case of a branch, well, we have two situations. Either the branch is not taken or the branch is taken. In the case of a branch which is not taken, well, when we have a hit, okay, so 90% is the hit rate. So the branch will be mispredicted if the branch is found inside the branch target buffer. So the hit rate here is given as 90%, and the branch is predicted to be taken. So the true outcome of the branch is not taken, but we are mispredicting it to be taken. So first we are going to hit in the branch target buffer, and the hit rate is 90%. And next we are going to look at the misprediction. Okay, the misprediction. So the prediction accuracy is 80%. So therefore, 20% of the time we are going to have a misprediction. So we are going to predict the branch to be taken, whereas the true outcome is that the branch is not taken. So 5%, okay, are the branches which are not taken. 90% of the time we are going to hit, and 20% we are going to mispredict. We are going to predict the branch which is not taken. We are going to mispredict it to be taken. And therefore the penalty will be 3 cycles. In the case of branch taken, we have two scenarios. So we have 15% are the branches which are taken. We have two cases. Either we have a miss, okay, in the branch target buffer. So we did not really find this branch instruction in the branch target buffer. So therefore we are not going to branch, although we are supposed to branch. So here we have a misprediction. Or the branch was found, okay, so 90%, okay, is the hit rate. So the branch was found, the entry was found in the branch target buffer, but we have mispredicted the branch to be not taken, although the branch should be taken. So we have these two cases, and then we multiply by the penalty, which is equal to 3 cycles. Now, if you look at all of these numbers and you add them up, you get actually 0.16. So they add up to 0.16. So therefore, now the new CPI will be 1.16. So we can see that the branch prediction scheme gives us the lowest CPI and the best performance. So in summary, we have seen 3 different types of pipeline hazards. We have seen structural hazards, we have seen data hazards, and we have seen control hazards, which are due to control instructions, the jump and the branch instructions. Now, hazards are going to limit the performance of the pipeline. They are going also to complicate the design and implementation of the pipeline. We have seen structural hazards. These can be eliminated by careful design or sometimes by adding more hardware. Okay, so this is why we use a split cache, a cache for an instruction cache and a data cache, so that both can be addressed at the same time to eliminate, okay, structural hazards. Okay, so also we have done the write back in the last stage of the pipeline so that to eliminate the structural hazard. We have seen data hazards. These data hazards are caused by data dependencies between instructions. We can eliminate data hazard by using forwarding. So we have to use additional buses in the data path, okay, for forwarding. Also, we have to use a hazard detection logic to detect that we have read after write and to implement forwarding properly. So this is going to complicate the implementation of the pipeline. Sometimes forwarding does not really work. In the case of a load instruction, okay, so the load instruction takes place in the data cache, and sometimes we are forced to stall the pipeline. So sometimes we have to stall the pipeline, waste clock cycles, and therefore this is going to increase the CPI. We have seen control hazards. We can use delayed branching. This can help to reduce the branch delay, but this requires a new meaning for the branch instruction and the support from the compiler. Branch prediction schemes work best if we use a branch target buffer in the first stage of the pipeline. We can reduce the branch delay to just 0. And we have to deal with branch misprediction. We still have to verify that the branch was predicted correctly. In the case of a branch misprediction, we still have to kill those instructions which are wrongly fetched. and therefore we waste clock cycles only when we have a branch misprediction. Okay, so that's it for this presentation. Thank you for watching.